All right, today we're going to be talking about Thevenin and Norton equivalent circuits with dependent sources present. So a lot of this is just going to be the application of what we learned in Monday's class meeting. But when we get specifically to determining the equivalent resistance of a network containing a dependent source, that's where things are going to get a little bit tricky. And so we're going to focus most of our attention there. So let's start with an example problem. So let's say that we have the following circuit where we have a 20-volt source in series with a 6-ohm resistor in series with a dependent voltage source where the voltage source has a value of twice Ix. Our current Ix will be the current that is flowing down through an 8-ohm resistor here. And then lastly, I'm going to put a 10-ohm resistor on the top right, like so. Let's call this terminal A and terminal B. And our goal here is to determine the Thevenin and Norton equivalent circuit seen between terminals A and B, where we are going to assume that the positive polarity terminal is on top and the direction is down for our Norton current. So if we wanted to find the Thevenin voltage for this network, we would simply place a positive polarity terminal at node A and a negative polarity terminal at node B, and then figure out what that voltage is. So I'm going to redraw our circuit really quickly. And I'm going to ask you guys how you might go about solving this. So any thoughts on how we might solve for our Thevenin voltage VTH here?
Nodal.
So we definitely could use nodal. I see 1, 2, 3, 4, possibly 5 nodes total. So that might be a little aggressive. Any other thoughts? So, I'm sorry, go ahead.
Mesh analysis.
Mesh analysis. So I'm hesitating here because there's only one mesh current because our right hand thing isn't a closed path. So it's not really mesh analysis so much as it is Kirchhoff's voltage law, which is what I was looking at. So let me explain why I think Kirchhoff's voltage law would probably, or actually, it's going to be Kirchhoff's voltage law and Ohm's law would be the best way to do this. So hopefully, we can all see very easily that the voltage drop across the 10 ohm resistor in this case is most definitely 0 volts because the 10 ohm resistor here on the right is not part of a closed current carrying loop. So if there is no voltage drop across the 10 ohm resistor, then I believe we can say that our Thevenin voltage is simply the voltage drop across the 8 ohm resistor. Just to make things incredibly clear here, we are saying that no current can branch off and flow to the right through the 10 ohm resistor because it's not a closed path. So that means that the current flowing through this region of the circuit must also be Ix. So if we were to write a Kirchhoff's voltage law equation, KVL around our left-hand loop, what we would wind up getting would be negative 20 volts plus 6 ohms times Ix minus twice Ix plus 8 ohms Ix is equal to 0. And we can rearrange this pretty easily, I believe, to say that, let's see, 6 plus 8 is 14 minus 2. So that looks like 12 Ix is equal to 20 volts. Therefore, Ix is 20 volts over 12 ohms. So that's going to be, let's see, 10 over 6 or 5 over 3. I think, right? Dividing by 4, divide by 4, yeah. 5/3 of an amp. And then using Ohm's law, VTH is just 8 ohms times Ix. So that's going to be 40/3 of a volt. Anybody have any questions, comments, or concerns about the analysis that we did here? There was nothing wrong with the suggestion of nodal analysis, but I felt that that was just too much work to get something that we could get, I believe, in a much simpler way. All right, so if we're all satisfied with our analysis for VTH, then let's find I naught. So our Norton current is found by shorting our terminals of interest. So I'm just going to redraw my circuit. And now between my terminals A and B, I'm going to place a short. And my Norton current is going to be the current that is flowing down through my short circuit. This current right here is still Ix. So how might we go about solving for our Norton current?
Mesh analysis.
So mesh analysis seems like a perfectly reasonable thing uh, to me here. Um, just because the only other way I could think about doing things would be to be, even then, that would be harder to do. I thought about combining a 10 ohm resistor and the 8 ohm resistor to find the voltage drop across those two elements because they're in parallel. And then if we divided that voltage by 10 ohms, that would be our Norton current. But as soon as we combine those resistors, we would lose our controlling current IX, which would make it not a particularly good method. So mesh analysis seems like a pretty good method to use here. So I'm going to call this mesh current IA, mesh current right here, IB. So KVL around mesh A is going to give us negative 20 volts. Actually, I'm doing things in the wrong order. I apologize for that. My controlling variable, IX, in terms of my mesh currents is going to be IA minus IB. Now I can set up my KVL equations. I apologize for doing things in the wrong order. So that's going to look like negative 20 volts plus 6 ohms IA minus twice IX plus 8 ohms IA minus IB is equal to 0. And then we could write a KVL equation at mesh B. So that would look like 8 ohms IB minus IA plus 10 ohms IB is equal to 0. And we now have 3 equations and 3 unknowns. So I'm going to be lazy and just solve this as a 3x3 system. So I'm solving for IA, IB, and IX. So rearranging my first equation, I have a coefficient of 1 for IA. The coefficient for IB is -1, and the coefficient for IX is also -1. When I move IX to the other side of the equal sign, my constant term is 0. In my second equation, my coefficient for IA is 6 plus 8. My coefficient for IB is -8. My coefficient for IX is -2. And my constant term is 20. In my third equation, my coefficient for IA is -8. My coefficient for IB is 8 plus 10. My coefficient for IX is 0, and my constant term is 0. And when I solve this system, I get 15/7 of an amp for IA, 20/21 of an amp for IB, and 25/21 amps for IX. Which of these current, so first actually, let me ask, if anybody did this in their calculator, did they get a similar result?
I got the same thing.
All right, thank you for that, Baylor. So which of these 3 currents, or how am I going to combine any of these 3 currents to find my Norton current?
IB equals I Norton.
Exactly right. So IB is exactly the same as I Norton. Okay. And from this, we could just say that R Thevenin is the ratio of our Thevenin voltage to our Norton current. So let me scroll up here really quickly. So 40/3 of a volt divided by 20/21 of an amp. Let me throw that in my calculator. That comes out to be 14 ohms. So that's the result that we got by taking the ratio of the Thevenin voltage to the Norton current. Now, it would be nice if we were able to verify that this is correct. Okay, so let's call this finding RTH directly. Okay, so we know that when we're trying to find the Thevenin equivalent resistance of a network, we need to look into the terminals of a dead network and see what resistance it is that we see. So I'm just going to redraw my network really quickly. So I turn my 20-volt source off, so that's why I've replaced it with a short circuit. Here's my 6 ohm resistor. Unfortunately, I cannot turn off my dependent source, so it's still going to be in there. Here's an 8 ohm resistor. Here's our 10 ohm resistor. And then here are our open circuit terminals. So we have a little bit of a problem here, in as much as we have a dependent source still in our network, which means we probably can't just do simple resistor combination techniques, right? So, for example, if we just assumed, let me put IX here, if we assumed that we could turn off our dependent source, or twice IX is equal to 0. By the way, there's really no reason that we can assume this, but as students who are first being introduced to things, this would be a very common mistake that I've seen you guys make. Just turn off the dependent source as well and just hope for the best. So if we assumed that was the case, then RTH might be 10 ohms plus 8 ohms in parallel with 6 ohms, which would come out to be 10 plus, let's see, 8 times 6, I think is 48 over 14. $240 over 7 ohms, or oops, I did 10 times, not 10 plus. My apologies there. Oops, and my finger grazed something. That seemed way too large. Sorry about that. 10 plus 48 over 14, 94 over 7. That seems a little more in the correct ballpark. And that is 13.429 ohms. So that's kind of close, but it's definitely not exact. So I hope that just ignoring the dependent source in this case is quite obviously the incorrect move here. So what we're actually going to wind up doing is essentially we're going to use Ohm's law. Okay? So I hope you guys can recall from our third lecture in this class where I said that if we have a black box network like so, and we were to excite this network, doesn't matter if it's a voltage source or a current source, we measure the voltage drop across the terminals of the network. We measure the current flowing into into the network, the resistance of the network is simply the ratio of the voltage across the terminals of the network divided by the current flowing into the network. So what we're going to do is effectively we are going to excite this dead network with either a voltage source or a current source. And then we're going to find the voltage drop across the terminals, the current entering the terminals of the network, and take that ratio to get our Thevenin resistance. Because Ohm's law literally tells us that we can do that for any circuit to find its resistance. Okay. So I'm going to call this applying a test voltage source. So I'm taking my dead network representation, and now I'm going to apply a voltage source across this set of terminals. So let's talk about the rules here. Effectively, there aren't any. And so what I mean by that is it does not matter what polarity our voltage source has, nor does it matter what the value of our voltage source has. So I typically am lazy and just say it's a 1-volt source. Nothing special about this value whatsoever, just literally being lazy. And I usually put the positive polarity terminal on top, but sometimes I don't, just whatever suits me. So I'm just going to arbitrarily assign a 1-volt source across my terminals A and B. Let me label those really quick. And my goal is to figure out the test voltage applied across my terminals and the test current flowing into the terminals of my network. So whenever I apply a test voltage source, then V test is a fixed quantity. In this case, V test is simply 1 volts. Let me just make a note out here to the side. RTH is simply going to be the ratio of V test to I test. So that's going to be 1 volt divided by something that we have to determine. So how might we solve for the current I test?
Mesh.
Mesh, sure, why not? So let's call this current IA, this current IB, and I did it again. Our controlling variable IX is just going to be IA minus IB. KVL around mesh A is going to look like 6 ohms IA minus twice IX plus 8 ohms IA minus IB is equal to 0. And KVL around mesh B is going to be 8 ohms times IB minus IA plus 10 ohms IB plus 1 volt is equal to 0. And now I'm going to solve this system for IA, IB, and Ix. So in my first equation, my coefficient for IA is 1, my coefficient for IB is -1, my coefficient for IX is -1. In my second equation, my coefficient for IA is 8 plus 6. Sorry, in my first equation, my constant term was 0. In my second equation, my constant term for, excuse me, my coefficient for IA is 8 plus 6, or 14. My coefficient for IB is -8. My coefficient for IX is -2. My constant term is 0. And in my third equation, my coefficient for IA is -8. My coefficient for IB is 8 plus 10, or 18. My coefficient for Ix is 0, and my constant term will be -1 when I move it over to the other side of the equal sign. And in solving this, I get IA is -1/28 of an amp. IB is -1/14 of an amp. And Ix is +1/28 of an amp. So how do these currents relate to our test current?
Negative IB will equal I test.
Exactly right. So this is just negative I test. So up here, we would have positive 1/14 of an amp, and 1 over 1/14 is 14. So applying a test voltage source got us the exact same answer that taking the ratio of the Thevenin voltage to the Norton current gave us. So this is a valid method. Just for the sake of argument, let's see what happens if we were to apply a test current source. So, redrawing my circuit. Across terminals A and B, I'm now going to put a current source. And again, doesn't particularly matter what the magnitude of my test current source is or the direction of my test current source. I'm just going to arbitrarily choose 1 amp, direction up. This is still my voltage V test. This is still my current I test. Once again, our Thevenin resistance is going to be the ratio of V test over I test. And in this case, my I test is very obviously 1 amp. And now my goal is to solve for the voltage V test. So how might I go about doing that?
Nodal.
All right, so let's look at nodal really quickly. So I'm just identifying my nodes here. So I have this big node on the bottom. I've got a node here, a node here, and a node here. Which of these nodes would you like for us to use as our ground or reference?
Do the bottom one.
Okay. All right. So we have, oh, let me label my nodal voltages then. So let's call this VA, this one VB, and this one VC. Let me scooch that over just because it's getting kind of busy. So how am I going to express my controlling variable IX in terms of my nodal voltages?
Be VB minus 0.
So VB minus 0 is a voltage, and I'm looking for a current. So you got to add one more thing.
VB over 8.
Exactly right. So VB over 8 ohms. Okay. I have a voltage relationship equation because there is a voltage source. So I'm going to have twice IX is equal to what? Somebody tell me what's going on here.
You'll start at the positive terminal, so it's just going to be VB minus VA.
Exactly right. I do have a super node that does not contain ground, right? Anywhere that I have a voltage source, I will have a super node. This one doesn't contain ground because it contains node A and B. So I'm going to have to add this current plus this current plus this current together. So my KCL at supernode AB equation. I think it's been a moment since we've done nodal analysis, so could one of you guys help me out here?
VA over 6 ohms
All right, so I agree with that.
plus VB over 10. Or VB minus A. Oh, VC. Oh.
Yep,
VC.
no, that's confusing because
Yeah.
that terminal is labeled as A, but I know what you meant. That's why I started.
Yeah. All right.
So my apologies on the confusion and labeling there. But VB minus VC over 10 ohms, definitely correct. And then the current
Plus,
down,
yeah.
which
It's
we
VB
already
over 10.
know to be VB over 8. Yep. And then what's the last thing that we need to do? I believe we're going to have to do KCL at node C. So KCL at C, what's that going to look like?
VC minus VB over 10 ohms. And then minus 1 amp.
So VC minus VB over 10 ohms minus 1 amp is equal to 0. Absolutely. So I have 4 equations and 4 unknowns, and I'm trying to decide what substitution allows me to be the absolute laziest, because that's how I prefer to do these things. So, for instance, if I rearrange this guy right here, I could say that VC minus VB over 10 ohms is equal to 1 amp. That's just moving that 1 amp over to the other side of the equal sign. If I multiply both sides by -1, that's going to give me negative VC plus VB over 10 is equal to -1 amp. And negative VC plus VB is the same thing as VB minus VC over 10. So realistically, I could scratch this thing out right here and replace it with -1 amp. And I now have a 3 equation, 3 unknown system where my unknown quantities are VA, VB, and IX. That being said, the voltage VC is the thing that I'm interested in. So maybe that's not the best substitution to make. So let me scratch that out. Sorry, we're just thinking out loud here. So it looks like we're going to have to be making our substitution with IX, which isn't particularly bad. So let's make our substitution in this one, right? So twice IX is 2 VB over 8 ohms will be equal to VB minus VA. Let me go one step further. So that's going to look like negative VA plus 1 minus 2/8 VB is equal to 0. Did I rearrange that correctly?
Yes, sir.
Okay, so we've got one equation, two equations, and three equations. So we'll solve this system for VA, VB, and VC. Okay, so in my first equation, my coefficient for VA is -1. My coefficient for VB is 1 minus 2 over 8. My coefficient for VC is 0. My constant term is 0. In my second equation, my coefficient for VA is 1 over 6. My coefficient for VB is 1 over 10 plus 1 over 8. My coefficient for VC is -1/10. My constant term is 0. In my third equation, my coefficient for VA is 0. My coefficient for VB is -1/10. My coefficient for VC is +1/10. And my constant term is +1. And when I solve this, I get VA is 3 volts, VB is 4 volts, and VC is 14 volts, where VC is the exact same thing as V test. So I'm going to have 14 volts over 1 amp is equal to 14 ohms. And once again, we got the exact same answer that we got earlier using both a test voltage source as well as the ratio of our Thevenin voltage to our Norton current. So the test source method doesn't matter if we use a voltage source or a current source. Doesn't matter what our polarity for the voltage source is, what our magnitude for the voltage source is, what our direction for the current source is, what our magnitude for the current source is. We are going to get the correct answer. One thing that I just want to point out and make very, very clear is that in order to employ the test source method, we have to be looking at a dead electrical network, meaning none of our independent sources are on. Okay. So this is how we are going to handle Thevenin and Norton equivalent circuits with dependent sources. Okay. So before we take a crack at our in-class assignment, does anybody have any questions?
Is there any situation where one of these would be easier than the other?
Absolutely. So let me look at the in-class assignment problem really quickly. And let's look at problem 2. So in this problem, we are specifically asked to use the test source method to determine the Thevenin resistance seen between terminals A and B of this particular circuit, right? So we know for sure we're supposed to use a test source method because we're just looking for resistance directly. So for this particular problem, I personally would choose a test current source, okay? So I'm going to choose direction up, and because my resistor values are on the kilo ohm scale, I'm going to choose 1 milliamp as my test source. just so that my voltages aren't like in kilovolts. So let me explain my reasoning for choosing a test current source here. Now, there is a fixed amount of current, 1 milliamp, flowing in, and it's flowing in and through this 1.6 kilo ohm resistor. So the voltage Vx is essentially a known quantity because 1 milliamps times 1.6 kilo ohms gives me 1.6 volts, which means this 2Vx thing over here is now just 3.2 volts. So by choosing a current source, I get to make my controlling variable a constant, which means I made my system or whatever I need to solve this thing easier. You will not, there's not always going to be an obviously better choice. And in some cases, there literally isn't a better choice. But if you can apply a test voltage or test current source that makes your controlling variable well defined, then use whichever one does that. And if you can't do that, then whatever way floats your boat works, because either one is equally valid. Does that clarify things a little bit or answer your question?
Yes, it does.
Okay, so let's go ahead and finish working on this particular problem since we've already got roughly half of it done. Okay, so here's the test voltage that we are trying to solve for. How might we go about doing that?
I'd say mesh is probably easier.
I would go to mesh.
Okay, so let's use mesh then. So let's call this mesh current IA and this mesh current IB. We no longer need a controlling variable relationship or anything like that because we know exactly what it is. It's 1.6 volts, and we've already applied it to our dependent source to make it effectively just an independent source now. So we do have a current source, so we're going to have a current relationship equation. So how does the, 1 milliamp of current relate to our mesh currents?
1
Just
milliamp.
equal IA.
Yeah.
Exactly right. So now we're just going to write a KVL equation around mesh 2, or excuse me, mesh B, and then we should be good to go. So around mesh B, we're going to have 8.4 kilo ohms times IB minus IA plus 7.5 kilo ohms times IB plus 3.2 volts is equal to 0. And we're going to solve this system for IA and IB, and this is very obviously going to be 1 milliamp. I am lazy enough to just leave this as a 2x2 system and let my calculator do the work. So in my first equation, my coefficient for IA is 1. My coefficient for IB is 0, and my constant term is 0.001. In my second equation, my coefficient for IA is negative 8400. My coefficient for IB is 8400 plus 7500. And my constant term is negative 3.2 volts. Solving this system, I get IA is 1 milliamp and IB is 0.327044 milliamps. Our Thevenin resistance, actually, hold on. So that's what our IB is. How do we find V test from this?
We'll do a KVL around IA.
So we could do a KVL around IA. We could also do a KVL around the outside. Either of those is valid. Because you suggested KVL around mesh A, let's do that. So we're going to have V test is equal to 1.6 kiloohms. Actually, we don't even need to do that because we know it's 1.6 volts. 1.6 volts plus 8.4 kiloohms times IA minus IB. So let's do that. 1.6 volts plus 8.4 kiloohms times IA minus IB. One of the reasons I love the TI calculators is because they automatically store those variables in your memory when you solve the system. So to me, this is going to look like 1.6 plus 8,400 times x minus y. And I get 7.2528 and some change volts. And from this, R Thevenin is 7.2528. So let's just call that 7.253 volts divided by 1 milliamp comes out to be 7.253 kiloohms, exactly what we were expecting. Just to be clear, we definitely could have used a test voltage source and we would have wound up with the exact same answer. But in this case, the test current source made things significantly easier. Any questions on this one before we jump back to problem 1? Alrighty. So in this particular problem, we are asked to determine effectively the Thevenin and Norton equivalent circuit seen by the load resistance RL, which means we're going to wind up taking that load resistance out of our circuit to determine our quantities. Okay, so finding VTH. So I've got a 12-volt source. Then I have a 6.3 kilo ohm resistor. Here's the terminals where RL was. I have to take it out. This is where my Thevenin voltage VTH is going to be. This is 0.5 Vx. Then I have a 2.8 kilo ohm resistor. Two milliamp current source. A 1.1 kilo ohm resistor. And then the voltage Vx is defined to be the voltage drop across that 1.1 kilo ohm resistor. So what circuit analysis technique do you guys think we should use to find VTH?
Nodal.
So we could definitely do nodal. Let's just look at things here really quickly. So I've got one node here, a second node here, a third node here, a fourth node here, and a fifth node down here at the bottom. So that's going to be a pretty darn large system. So we could do it, but we only have 2 meshes, so I think that might be the easier route. So if we were to apply mesh analysis, we would have this mesh we could call IA, and this one over here would be mesh B, right? We have a controlling variable. So what would Vx be in terms of our mesh currents?
Negative IA? Oh no,
So-
positive IA. Sorry.
So Vx is positive IA. I disagree with lots of things there. How is voltage current?
I would say 1.1 kilo ohms times IB.
I agree with that one, right? So just using Ohm's law, the current that's flowing into the positive polarity terminal, the 1.1 kilo ohm resistor is IB. So 1.1 kilo ohms times IB seems like a perfectly reasonable expression for our controlling variable Vx. We have a current relationship equation because there is a current source. So we're going to have 2 milliamps is equal to what?
IB minus IA.
Exactly right. And now we're going to write a KVL equation effectively around the outside loop of the circuit. So KVL around super mesh AB is going to look like negative 12 volts plus 6.3 kilo ohms plus 2.8 kilo ohms times IA plus 1.1 kilo ohms times IB is equal to 0. And so these two equations together give us a 2-equation, 2 unknown system that we can solve for IA and IB. So I'm going to do that really quickly. My first equation, my coefficient for IA is negative 1. My coefficient for IB is positive 1. And my constant term is 0.002. And my second equation, my coefficient for IA is 6,300 plus 2,800. My coefficient for IB is 1,100. And my constant term is positive 12. When I solve this, I get 0.96078 milliamps and 2.96078 milliamps for IB. So now solving for VTH, if I were to do a KVL around this purple path here, I would have negative 12 volts plus 6.3 kilo ohms times IA plus VTH plus 0.5 Vx, where we know Vx is 1.1 kilo ohms times IB is equal to 0. Rearranging really quickly, our Thevenin voltage would then be 12 volts minus 6.3 kilo ohms IA minus, let's see, half of 1,100 is 550. So I'm just going to throw this into my calculator. So here, 12 minus 6,300 x minus 550 y gives me 4.3186 or 4.319 volts, which is exactly what we were expecting. We definitely could have done the nodal analysis, but it was just so many nodes that we would have to make several substitutions, and it just seemed like more work than it was worth to me. So, any questions on how we solved for VTH here? All right, so I am going to erase this. So we know that we solved for VTH correctly. Let's see, remove all annotations. And now we're going to work on part B. So in part B, we're just going to replace that resistor RL with a short circuit. So we've got our 12-volt source, 6.3 kilo ohms. There's our short. Here's our dependent source, 0.5, sorry, VX. I believe this is 2.8 kilo ohms. 2 milliamps, 1.1 kilo ohms. Sorry, my penmanship is getting crappier than usual. And then here is our voltage Vx. Our Norton current is simply the current that's flowing down into the positive polarity terminal of our 0.5 Vx source. So what analysis method might you guys suggest to find I Norton here?
I'd probably say mesh.
So mesh looks like an obvious solution. Let me just think about this really quickly. So right now we have 1, 2, 3, 4 nodes, one of which would be ground. I personally would probably choose ground to be the bottommost node, which means that the voltage at node 1 is just 12 volts, so it's a constant. So really, the voltage at node 2 and the voltage at node 3 are the only unknown quantities. So I know this is probably going to piss you guys off, but I would actually probably do nodal here, even though I'm trying to find a current, because the system is simpler to do. And we'll do mesh anyway. I don't want to be just contrary for the sake of being contrary all the time. So let's call this IA, IB, and IC. What's our controlling variable relationship going to look like?
1.1 kilo ohms times IC.
Yep, exactly the same thing as it was before. And then our current relationship equation should be exactly the same thing as well. So that would be IC minus IB. Now we're going to do KVL around super mesh BC. So that's going to look like negative 0.5 Vx plus 2.8 kilo ohms IB plus 1 kilo ohms IC is equal to 0, and then KVL around mesh A. would be negative 12 volts plus 6.3 kiloohms times IA plus 0.5 Vx is equal to 0. And so if we substitute in V 1.1 kiloohms times IC everywhere that we see Vx, we have this equation is number 1. Let's play with this one a little bit. So we have negative 0.5 Vx, which is negative 550 times IC. So let's see, 2800 IB plus 550 IC is equal to 0. If I did my algebra there correctly, if I messed it up, please let me know. And then down here, we're going to have 6300 IA plus 550 IC is equal to 12. So this is our second equation and our third equation. Let's solve these guys. So in my first equation, my coefficient for IA is 0. My coefficient for IB is negative 1. My coefficient for IC is positive 1. My constant term is 0.002. In my second equation, my coefficient for IA is 0. My coefficient for IB is 2800. My coefficient for IC is 550. And my constant term is 0. And in my third equation, my coefficient for IA is 6300. My coefficient for IB is 0. My coefficient for IC is 550. Constant term is 12. Solving this, we get IA is 1.7588 and some change milliamps. IB is negative 0.328 and some change milliamps. And IC is 1.6716. What would I Norton be in terms of those mesh currents?
IA.
IA minus IB. So I'm going to go ahead and throw that into my calculator as X minus Y. And I get 2.0872 milliamps, which seems to agree. Any questions about how we used mesh analysis there to solve for our Norton current? All right, so just because there's not a lot of room here, let's go ahead and remove all these annotations again. Now we're working on part C. We want to determine the Thevenin resistance seen by the load. So RTH should just be VTH over I Norton, which should come out to be 2.069 kiloohms, just based on using these numbers here. That's a pretty straightforward calculation. How would we determine the maximum power that could be transferred to the resistance RL by the circuit?
Would this be I Norton times VTH?
It would not. So if you recall from our discussion on the maximum power transfer theorem, it's going to be 1/4 the source voltage squared divided by the resistance of the source which is going to be the same thing as 1/4 times our practical source current squared times the resistance of the source. Well, our practical voltage source is just our Thevenin equivalent circuit, and our practical current source in this case is just our Norton equivalent circuit. So really, we could just say this is 1/4 VTH squared over RTH, or 1/4 I Norton squared times RTH. Either way will wind up giving us the same result. So if we substituted in those numbers, that would look like 1/4 times, let's do this, 2.087 milliamps squared times 2.069 kiloohms. So 0.25 times 0.002087 squared times 2.069 times 10 to the 3. We get 2.253, 2.252918, whatever. So 2.253 milliwatts, which agrees with our answer here. So unfortunately, VTH times I Norton is still meaningless. Anytime we're asked for maximum power, we're always going to go back to those maximum power relationships. But now we know that all of those simplifications that we did to get things down to a practical voltage source in series with our load resistance, or a practical current source in parallel with our load resistance, that is the exact same thing as just finding the Thevenin equivalent connected to the load resistance, or finding the Norton equivalent circuit connected to the load resistance. Which is why I think that that lecture on just doing strict source transformations is utterly useless, because we now have a better method of doing that that doesn't require us to have rules. So anyway, just the rantings of an old man. Any other questions regarding Thevenin and Norton equivalent circuits? All right, well, we wrapped up a little bit early today. I don't have a problem with that if you guys don't. I hope you all have a happy and safe 4th of July, and I will see you on Friday afternoon for those of you that aren't too hungover or too sunburned from the lake or whatever.
Have a good 4th of July, Dr. Hartman.
You too, Austin. Thank you.